In our last class, we talked about electric field strength and had an equation to calculate how strong a field would be around any source. And that equation, again, is E equals Kc times the source charge, Q, over the distance squared, where again, Kc is Coulomb's constant, which is the value 9 times 10 to the 9 Newton meters squared per Coulomb squared. So if I have any source and that anywhere around that charge, you would have a field. And as you get closer to that field, the magnitude of it gets stronger, right? And as you get further away, it gets weaker. And the larger the charge, the greater that field strength is. And again, this is a vector quantity, so we got to keep in mind the direction. And this is really similar to what we've done already with gravity. So hopefully this element is review. And we did an example where we found the strength of the field. Now, where we get a little more challenge is when we start to realize that, well, there sometimes can be multiple charge sources that are creating a field. And it happens simultaneously. So when we have multiple sources, just like if we had multiple planets, and we did this with the Earth and the Moon, I believe, you would have two fields. With multiple sources, you have to consider the combined fields of those two sources. So we need to consider the combined effects the combined fields of the two sources, or more sources. And so if I placed an object somewhere around those sources, it's going to feel effects from both of those, or 3 or 4, or however many sources you have. And so we have to look at this total field. E total is what we would call the net, or the total field strength. Is just going to be the vector sum of however many fields you have. Field A plus field B plus however many fields you have. We go field N. Right? So we just add them all up. And again, these are all vector quantities. Right? So we add them as vectors. So it's important that we keep track of the direction. So the direction is important. So let's look at an example where we have to add a couple fields together. And you'll see how this comes into play. So in our example problem, we have two sources. Let's say these are balloons that are rubbed with electrons. Right? And one of them you rubbed a little bit more vigorously, so it picked up a few more electrons. Right? So we have two balloons. We'll call one source A, and that balloon picked up some electrons and is now carrying a charge of negative 20 microcoulombs. And the second balloon, we'll call that source B, is charged with electrons as well, and it picked up even more. And as a result, due to all those electrons, it has a charge of negative 60 microcoulombs. And those two balloons are a distance away from each other. They are 50 centimeters apart. And what I want to know is if I brought some particle in between those two, right at the midpoint, I want to know what is the total field halfway between the two balloons. What is the total electric field strength halfway between the two sources? So again, a typical problem. Some people call this a superposition problem because you're kind of superimposing two different fields together. Uh, so let's start to set up a problem. And as we've done throughout the entire year, it's really critical that our setup is right so we can calculate things. And a big part of the setup, particularly in this unit, is to get these arrows correct. And so drawing a picture is critical. So most people, I think, are going to draw A and B in some way, shape, or form like this, but actually how you draw it is not that important. Some guys might draw B on the left. I would suspect most would draw it this way. Now, I'm also going to color code this. I think it can help visually so you can really see things, but that's not that important. But in OneNote, I had this flexibility. And we know that charge A is negative 20 microcoulombs, and charge B is negative 60 microcoulombs, so a little bit stronger field. And we know that these charges are 50 centimeters apart from each other. And we're trying to evaluate what is E total at that position, right in the middle, which hopefully you'd recognize would be, and again, it's helpful to convert this to meters. We want everything in meters, kilograms, seconds, and coulombs. So I really have a half a meter, which means this is a quarter of a meter from here to here, and a quarter of the meter from here to here. And that's an important thing to recognize. Sometimes the number given in the problem isn't directly used in your calculations. You need to infer what that means. So at this midpoint, we effectively are trying to test the field right there. And we always test a field with the convention that we're bringing in a positive test charge that is infinitely small. So let's say it's the smallest it could be, which would be 1 proton. And so it's so small that it's really not affecting the field at all. It's just testing it. We wouldn't know that field is there until we put something in it. And so with that convention, we can then draw our field arrows. So this is where you have to look at those charges. So I have a negative charge from A and a positive charge for our test charge Q. So hopefully you realize, hey, opposite charges should attract. And so A should pull on Q to the left. So I'm going to draw an arrow and label it field of A. And that arrow should point towards A. Now B will also attract Q. And B is bigger than A. In fact, it's 3 times as big. So you might even draw it to scale, right? 1, 2, 3 times as big is the field of B. So I'll draw a nice big arrow that points towards B. And because we're adding vectors, my answer, the total field, should be the vector sum of A and B. And hopefully from the picture you'd identify, we are expecting an answer that is to the right. Towards B would be what we'd expect from our drawing. Well, now let's actually start calculating some things. So we have our field strength equation. And so what we need to do is figure out the magnitudes of each of these, and that's what that equation does. So the field strength of A is just equal to Coulomb's constant times the charge of A all over the distance from the test charge to A squared. And I can plug in my numbers. Kc, the Coulomb's constant, is always 9 times 10 to the 9, Newton meter squared per Coulomb squared. The charge of A is 20 microcoulombs. And so that's 20 times 10 to the negative 6 is micro. Again, nice little trick. I don't have to do any crazy conversions. I literally replace micro with times 10 to the negative 6, and now we're in coulombs. And the distance in the denominator to A is only a quarter of a meter. So I'll square that. Again, we want everything in coulombs, everything in meters. Notice I left out the negative sign. Most people, if they saw this number negative 20, want to plug it in as negative. Negative doesn't quite mean what you think it means anymore. It doesn't mean left or right or anything like that. It just means typically it will be an attractive force. But let's leave the sign out of our calculation, and we'll put in the sign later when we interpret what it means. So in my calculator, all right, the first thing I'm going to do is I'm going to put in K. Now, one thing you can do, we're going to use K a lot, which is 9 times 10 to the 9. And so you might want to store as K. And so now, when I just do alpha K, I have it here. It saves me 1 keystroke, maybe not a big deal, but it's a nice thing to have in your calculator. And so I can do alpha K times 20 times 10 to the negative 6 is just the double E feature, second double E, negative 6, and then divided by 0.25 squared. Missing some keystrokes here. And I get a value of 2,880,000. So 2,880,000 newtons per coulomb, or 2.88 times 10 to the 6 newtons per coulomb. All right. Let's find the magnitude of B. So the field of B, again, is Coulomb's constant, the charge of B, and the distance to B squared. Start plugging in our numbers. You'll notice it's pretty similar. This time it's 60 times 10 to the negative 6, all over 0.25 squared. And when you plug that into your calculator, again, the only thing that's changing is the charge. So I can do second enter to reload that equation. I'm just going to change this to 60. And I hope you'd recognize it should triple the number. And I get 8,640,000 newtons per coulomb. So those are the magnitudes. And now let's think about those signs. So this is where the picture is helpful. So I'm going to give a sign as if I'm putting it into an XY vector table, right? Remember, we always drew our force arrows, right? And then we put them in the XY table, and we use the picture to determine the sign in there. Well, let's use that again. The field of A points left. So I'm going to assign this one negative, right? The arrow in my drawing, the way I drew it, points left. And the field of B points to the right. So I'm going to assign it positive because the arrow points to the right. Again, we're adding vectors. We've done this before. Hopefully this is not something you got to jog your brain too much about. And so now all I have to do is add the numbers, right? And so if I take that number and I'm effectively subtracting this value, I get 5,760,000 newtons per coulomb, and it ends up being positive as I've calculated it here in my table. However, that's not really good enough in my answer. You need to be more specific because, yeah, you drew it, so I kind of know what you mean, but just saying, oh, it's positive, it's to the right. Positive doesn't really mean right in this case. We have to define that total field, we have to interpret what positive means. Well, the magnitude doesn't change. It's 5,760,000 newtons per coulomb. But what does positive mean here? Well, positive means to the right in my drawing, which means towards B. Or you could say away from A. That's how we have to define direction. Right? We're defining a vector quantity. You have your magnitude as the number part, and the direction is either towards B or away from A. Both of those would define exactly the same direction in this scenario. So again, a good example problem, a simple superposition example where we have two sources and we're finding the total field that exists in between those sources.